So thank you so much all for attending my oral defense. Very excited to share my work that I've been doing for the past 6 years or so. I will not talk about every single observation I have done. I don't know why this doesn't go away. Should go. So yeah, I will not be able to talk about everything because of time. So instead, I'll be focusing on yes, I will be focusing on main research questions, how I answered them, and how some of these research questions led to yet other kind of research questions. So I will be going through my research journey. And the first thing I thought about in my PhD was why debugging is hard, and I wanted to illustrate my understanding through an example. So imagine you're working on movie search app. You wrote a code that's supposed to work when you type a movie and click search. It's supposed to show a list of movies. However, you discover that that is not the case. When you type for example, Spider-Man, it doesn't show anything. So you may ask yourself, why? Why this is happening? Why you have this bug? You thought this is correct. To answer this question, you need to formulate hypotheses. And these hypotheses are really general speculation about why the bug might happen. So for example, you may say, maybe I did not parse the data correctly. And that's why when I click that button, it doesn't show any movies. So working from this hypothesis, here's a hypothesis debugging model that describes this process. You need to gather evidence. You need to go look at the source code that related to the parsing. You need to go and read documentation. You may need to set breakpoints to inspect the parsing data. But the ultimate goal is to test this hypothesis to confirm whether it is the correct hypothesis that explains the bug, or to reject it if you find otherwise. The challenge is, what if the hypothesis is incorrect, right? And you have this hypothesis, but really the cause is something else. Pretty much everything you will do to test this hypothesis may not lead to defects. And if you have so many incorrect hypotheses, you will find yourself spending hours and hours of debugging that ultimately did not lead to a fix, or you understanding the cause. Even worse, what if you don't have a hypothesis? In this case, you feel stuck. You will pretty much stuck in this step. You don't know what information you need to gather, what source code you need to inspect. And this is
I'm sorry. If I'm looking for a movie, can you help me understand how what the hypothesis is? That will help me understand the rest of your presentation. What's the debugging here?
So the bug is when you search for Spider-Man in that search engine with application. The bug is you don't get any results. You get an empty page. Is that clear? So you in the debugging process, you're just basically speculating and hypothesizing what might cause this bug, why the movies doesn't show up, even though you have written the code that you thought it should produce the correct output. So you're just investigating, trying to understand why the program is buggy.
Okay, thank you.
Okay, I'll give a few examples. The rest of the debugging I will show even a demo of my tool. So hopefully you'll understand the further in the presentation. But the bottom line is that hypothesis is getting the correct hypothesis is really central to debugging. If you don't get the correct hypothesis, if you waste time inspecting incorrect hypotheses, your debugging may not lead to a fix. So although this is kind of the hypothesis is very central to debugging, we got pretty much no support into it for it in terms of tools. There's no tool that directly support developers find and test these hypotheses. And instead, what you got, or what the most of the research community focus on, is this notion of fault localization. And fault localization has this assumption that is, if we help developers really point to or find the buggy line faster, they can look directly to the bug and know what is the bug and fix it. They don't need to go through this process of hypothesizing and testing. They need just to look at the source code and fix the bug. That's kind of the implicit assumption of the fault localization. I got so many tools that implement different techniques. So you have an example here where a fault localization tool highlights and ranks suspicious line of code based on, some sort of testing and information about the tests. But essentially, you get a rank list of most suspicious line of code, and developers need only to focus on these, and hopefully they will look and localize the bug and fix it without any hypothesis. This is kind of the underlying assumption of fault localization. So the first question I had in my PhD when I looked at these different things, I was thinking like hypothesis seem very central to debugging, but we don't have enough support to it. However, there's this focus in fault localization. If we compare tools that offer developers fault localizations to tools that help developers find and test hypotheses, which one is more effective? And essentially, my goal was to determine my rest of my PhD work. If I found out that localizing the defect of localization is more effective, then I may go and proceed my work in that direction, or go work in exploring this idea of supporting developers find that this hypothesis. So to answer this question, I did a randomized control experiment. I recruited 20 participants, and the idea of this experiment is basically simple. I recruited 20 participants, I give them 3 debugging tasks. I randomly assign this, what I call debugging aids, which is a potential hypothesis, a list of potential hypotheses, a list of fault location, and nothing. So I randomly assign these debugging aids to developers through the 3 debugging tasks and study their impact on the debugging success. And here's an example of what fault localization aid look like. It's just a bunch of lines of code taken to developers. Hey, go look at line 15 or line 25, and one of these has the bug. Or I give them a list of hypotheses that generally explain the bug. There is no implementation detail in these. So you are not binding the scope of this to the callback. This might be causing the bug, and a general way to test this hypothesis, all in text. And I built a platform for this study. So I built this website that has this, I hate this zoom, that have the description and the IDE that where developed participants can debug the program. And then I offer them the debugging aid in this interface where they can see either a list of hypotheses or a list of fault. What I found that offering developers potential fault location made them 6 times more likely to fix the bug. And while offering them fault location did not offer any significant impact in their debugging success. And that led me to my thesis work and kind of the first insight I had in my PhD, which is basically offering tool support for hypothesis-based debugging that help developers find that this hypothesis can significantly improve developers' efficacy in debugging. And my goal from now towards is just to find and prototype and explore this idea of hypothesis-based debugging. But what is hypothesis-based debugging and how it should help developers find a fit hypothesis? This is a good idea, but kind of the implementation wasn't clear for me. And if we go look at this model of debugging that described the hypothesis-based debugging, it seems that it described the entire debugging process, the entire debugging behavior, starting from looking at the big reports, reading code, having a hypothesis, instrumenting, changing the source code, testing this hypothesis, and going in loops until the bug is fixed. So maybe a good way to start is to go and observe the developer while debugging and try to understand the entire behavior from the start to end. But I wanted to first to go and see if someone has done it before. So I went and did this kind of a survey in prior work debugging behavior. What I found that most of the prior work in understanding debugging behavior focus in this strategies, which is an instance of a behavior. For example, navigating backwards and forward. So it doesn't explain the entire debugging behavior, but instead focus on particular strategies. Also, there's been focus on how developers use the debugger. Debugger is essential in the debugging process, but it's not the debugging. Doesn't explain the entire debugging behavior from start to end. Also, I observed that most of the prior work either studied the debugging behavior through log analysis, so they instrumented the IDE and analyzed the logs, or through a control experiment, lab study. Only 5 studies that I found that did a direct field observation of developers working on in their typical environment without any kind of changes in how they work. So I wanted to study developers in their typical environment while debugging. So I wanted to study them while working without kind of lab or intervention. So to do that, I proposed the usage of live stream programming. We all know open source projects, right? Developers work in an open source project, and then they share the source code with the entire community. The live stream programming complements this. So open source developers do not only share their source code, but also stream their development of the open source project. And if you join a stream like in programming and Switch or YouTube, you will probably see something like that. You will see the development environment, the streamer, the developers, and a chat where the developer interact with other watching that developer working in open source project. So I went and studied that phenomena from different perspectives, but the ultimate goal was, is this representative for me to use it to study developers' behavior while debugging? So I went and have a number of live stream sessions, and I analyzed them, and I found that the developers in this session do write code, debug, navigate, read documentation. They also get interrupted, which you expect from developers in the office. So pretty much they behave exactly how developers behave in day-to-day work. We need to make sure that we don't, for example, include in our analysis this interruption, and make sure that developers work in open source projects while if we want to use these live stream as a source of information. So I went and built a platform for researchers to use this new source of information. It's observed that it's online. You could go and see it through this tinyurl.com/plateau, but I don't have time to show it today. But it is basically a way for researcher to accumulate these videos, to annotate them, to collaborate with other researcher, and share it with the broader community. So it's basically a platform for analyzing and sharing these videos. So I now have the data set for my observation, but what kind of behavior I want to observe? I mean, this kind of behavior, this question is kind of general and wanted to be more specific. So I had to go and look at this hypothesis-based debugging model yet again. The first thing I observed that developers do engage in various activities throughout this model. They set breakpoint, they read documentation, they edit code, and they run the program. So there is some sort of engagement in activities throughout the debugging. So the question I had, how do developers really engage with these activities throughout debugging? How these activities constitute debugging? That's kind of the first type of behavior I was interested to study. The second type of behavior is this edit run cycle, what I call it. You can see there's this loop of feedback where developers change, run the program, and move through it. So I was interested also to study the characteristics of these edit run cycles. These two kind of questions or studies turned to be two separate papers. So the first one is under review in the Empirical Software Engineering Journal. We're very due to the second round of revision. The other one was published in VLCC 2021 and won Best Paper Award. So let's focus on the first study. So I got this data set. I had 15 sessions, 11 professional developers working in big companies like Microsoft, Firefox. We have projects like Firefox and Curve, very popular open source project, along other different open source projects with different programming languages. So it's a diverse data set. And I went and annotated 89 debugging episodes. So I defined debugging episode as the moment where developers encounter a defect and start debugging until they either fix the bug or decide to stop debugging. So I coded 89 debugging episodes. I coded more than 20,000 debugging activities within these episodes. Let's see some interesting insights about these activities. So I can see this edit activities where developers change the code. Here's the percentage of the debugging episode, and you can see the frequency as developers edit code more often within the 10% until the 90% of the debugging episode. So it's
What's the x-axis here?
as the debugging episode kind of percentage. So
like time.
time, time. For the test is basically the opposite of, and then you can see that test developers engage with testing more often within during the start of debugging episode and the end of debugging episode, while this in the middle not so much. For the navigating, they engage more in navigating and start engaging less and less as the debugging episodes approach the end. For the inspect, where they inspect the code, it's like up and down, but it's more frequent in the middle of the debugging episode. And consulting is interesting to me because developers go and consult resources, Stack Overflow, read documentation, but you can see it's increased as did the debugging episode go, and then it topped here in the middle, meaning that developers most likely going to go and read documentation on Stack Overflow during the middle of the debugging episode, not the start. Maybe they doing other things before they go and read documentation. So that's one of the many insights I have with the debugging activities. The other insight I had was, if you look at the distribution of the debugging episode, it's skewed toward the right. So 75 of the debugging episodes were relatively short, where 4 minutes on average, where the 25% of debugging episodes were relatively long, and they consume most of the debugging time. So you could say that people and developers while working, they often encounter debugging work that is short and easy. That's the most common debugging type or episodes. But there are this infrequent debugging episodes they may encounter that's going to be very long and gonna consume most of their time. And I was interested to study how the debugging activity changed as the debugging episodes grow. So do developers really work in and engage with different activities in this 2 hours debugging episode, similar with this maybe few minutes debugging episode. So I went and created a correlation between the activities developers do, the fraction of the activities, and the episode length. And I found that developers engage more in navigating, more in inspection, more in consulting and other type of activities as the debugging increased in time. And they engage less in testing as the debugging episodes decrease. And pretty much the edit hasn't changed really. So there's the insight here is there's as the debugging increase in time, developers seem to be engaging more in these activities. Different types of these activities. Kind of this is the main insight I had from that study. For that edit run cycle, it's a very popular kind of behavior that's been studied by the live programming environment community, where the developers edit the code and run and see how their edit impacted the program, which is also fundamental to the hypothesis test model, debugging model. So I just pretty much used the same data set that I used for the first study. I just need to map these activities to either the edit or run steps based on how the live programming community defined edit or run steps. And for these activities that did not belong to either edit or run, I grouped them in category gaps. So I coded 581 cycles in debugging and 207 cycles in programming. And here's a few interesting insights about how developers engage in edit run cycles. So for debugging, these cycles were relatively short. They were 1 minute long. Compare how they occurred in programming. When they occurred in programming, they were on average 3 minutes long. Developers engage in 7 times cycling in debugging to fix the bug or decide to stop debugging. So on average 7 times cycling, where in programming they cycle on average twice before either encounter a defect, so they need to debug or they need to stop. Other insight is that developers spend most of their cycle time in the edit step. Most of their cycles contain one file change or one file edit. When they run the program, they mostly run it manually. And when they run the program to observe the output, they look for the final output and not the intermediate state. So the main observation here was that developers do engage in average 7 times per debugging episode, which is maybe a lot. So the goal of debugging hypothesis-based debugging tool may be to reduce the effort and time that developers need to collect all sorts of information and switch in between these activities. Because we observe that as debugging increases in time, developers do a lot of work switching between these activities. So maybe we need to decrease that amount of work and the need for switching between different tools and activities to collect information. Also, maybe we need to reduce the number or frequency of edit run cycles, either by helping developers identify the correct hypotheses faster, or have more better strategy in testing hypotheses, so that developers test the hypothesis and confirm or reject it from the first time, rather than maybe cycling due to flaw in the way they test the hypothesis incorrectness. But now these are great, but how I'm gonna build a tool that know which information is important to collect, how I am supposed to find the hypothesis, And it turns out the way expert developers do it is because they have knowledge, right? They have seen similar bugs, and by acquiring that knowledge, they know where to look and how to test the hypothesis. And if we need to effectively help developers in these steps, the debugger also need to have this important component of knowledge so that it knows where to look and what kind of strategy to offer and what hypothesis is relevant to that particular defect. With that, I would like to introduce this hypothesis-based debugger. So hypothesis-based debugger have basically 3 steps. No longer working. All right, so hypothesis debugger has 3 steps. Have this demonstration step where developers really reproduce the bug to the debugger, so it collect all relevant information during the reproduction step, and use that information to analyze the source code and other kind of events and internal value states to find the hypothesis, and then generate a testing plan for developers to test this hypothesis that the tool offers. And if you look closely, this is basically similar to the hypothesis-based debugging model, where the gathering context in the demonstration and identifying the hypothesis, and here it is testing the hypothesis. So it's basically mimicking this debugging model. So I implement this in Hypothesizer, which is a prototype for debugging web application. Let's see how Hypothesizer implement these steps. So for the demonstration steps, developers has this interface where allow developers to click record, and after clicking record, developers can reproduce and demonstrate the defect in a fully instrumented Chrome web browser that Hypothesizer control over the Chrome DevTool protocol. So basically, Hypothesizer collects all sorts of code got executed, events that triggered networking activities, interface events, changes in the interface. They'll collect all this kind of information automatically by just reproducing the bug. For the following, it's slightly more complicated, but I'll go through it step by step. So the demonstration step is the step we had. So the output of this demonstration step is what I call the program behavior. Program behavior looks like this. It has the kind of sequence of nodes that describe the program behavior through the recorded session. And each behavior, each node in this sequence describe different things. Line of code, as I said, events, networking activities, and their description is in a JSON format. So here's an example of that. So for a networking activity, it may say, this type of network, and it has this property, min type is JSON, locating the JSON, status is response received, and maybe the body and a timestamp. And the idea here is just to have a JSON representation of the program behavior that the hypothesizer can have, like analyze and understand. And now let's talk about the hypothesis dataset, which is kind of the knowledge component of hypothesizer, what really make hypothesizer act as an experienced developer. So it has this hypothesis dataset. It's fetched from within the project. So we hypothesizer expect that each project has this hypothesis dataset. Also, hypothesizer can be configured to fetch dataset from different sources in the internet. But hypothesizers loop over these hypotheses, and let's see an example of a hypothesis. So a hypothesis has a hypothesis which is a description of the bug, saying the data you receive from a server is not being parsed, resulting in the program not rendering anything. So this is a concise description of the hypothesis. and there's the description that contain more information. We have this two level of details about the hypothesis because we display them in different level of details in the interface, which I will give you example in a moment. And also have the symptoms. So the symptoms is basically describing the program outputs or what the developer observed as the bug. So for example, maybe for this clicking button not working, it says maybe is the symptom is rendering an empty page or unable to render anything, fetch anything from the server. And we will use that to further narrow down the hypothesis and collaborating with the developers. I'll give an example in a moment as well. And here's kind of the important part of a hypothesis, which I call like conditions. So each hypothesis has a set of conditions or a sequence of conditions that try to describe how a program may behave that make that a hypothesis relevant to that behavior. So it's described basically a instance of type of behavior that if it satisfied in the program, the original program behavior makes this hypothesis relevant. So for example, in here, in C, it says, you know, I expect after A and B satisfied, then there should be a networking activity with these properties. And there's this expected to be found, meaning that hypothesizer need to find this instant in the program behavior. Other condition maybe contain things like expected not to be found, and basically say that I expect the program behavior to not contain this type of condition. And if a condition is satisfied, meaning satisfied the program behavior, it represents a confirming evidence. If not, it's a contradictory evidence to the hypothesis. And I will show interface as well. But last piece is the how to fix, which is a general a description of developers to further test the hypothesis and maybe fix the bug. And it has this steps, and each step contains a text and an evidence related, which enable hypothesizer to be more specific to the program. So it's related to a condition here, but it should be satisfied. So it's a confirming evidence or a condition. I'll show an example as well. The other thing is a code template, which is describe a change that the developers need to introduce or remove from the source code. So either edit, adding more code, or removing the code as a code template. So after describing what a hypothesis looks like, hypothesizer extracts this condition from a hypothesis, from the every hypothesis, and construct some group patterns. So we use open source pattern matching engine called SemGrep that very effective in looking at source code or JSON and extracting properties or object that looks similar to the original object. So I will get this, for example, this condition and turn it to this YAML file using SemGrep. And then SemGrep will start conducting a query against the program behavior. And if it's satisfied and found it as expected, then it's a confirming evidence. Otherwise, it's contradictory. After having all this sort of querying and confirming and contradictory evidence done, hypothesizer categorize each hypothesis either as a confirming, as most likely hypothesis if it has 100% confirming evidence, or less likely hypothesis if it has more than 50% confirming evidence, but less than 100%. And if the hypothesis has less than 50%, hypothesizer disregard this hypothesis and not shown to develop. All right, that's a kind of quick overview of the idea of how the hypothesizer find relevant hypotheses. After this categorization, hypothesizer work with the developers to narrow down the hypothesis. So it shows the symptoms label that we just saw in the previous slide, that the developers ask developers to select which one is more representative of the symptom. And the reason we did not do this automatically, because this is somehow related to the developer's intention and not the bug. So maybe developer's intention is to render an empty page, but we cannot tell until the developer is saying this is a symptom of the bug. This is the bug itself, not something I expect. So by enabling to collaborate with hypothesizer can further narrow down the list of relevant hypotheses. After the selection, hypothesizer show that in a list here. So to test these hypotheses, developers need to click on one of these hypotheses, and that got show up the testing interface. Testing interface contains the hypothesis, the description we saw, and then there's this timeline of evidence, which basically the condition, but now they are evidence that either confirm, and they confirm if they have this clicking check mark, meaning this condition was satisfied. And then when a developers click on each of these elements in the timeline, it shows detailed information about that evidence. It shows line of code that related to that evidence. It shows internal program statement. For example, here it shows this networking activity saying, here's how the property of the response that received from the server, and this is the payload. Helping developers really inspect and test the hypothesis within one interface rather than switching between different activities. When developers click on the timeline evidence that contain the X here, this is where the hypothesizer show the how to fix part of the timeline, which contain, as I said, the steps of how to fix it. So for example, it says here, locate where the fetch API will be used in your code. Here's a potential location, and this location is based on one of these evidence in the timeline, so it knows where it is in the source code. And then it describes a change that developers need to do given a code template. And I want to also show you how a contradictory interface, contradictory evidence interface showing the timeline. So if developers click in the second hypothesis, which has one contradictory evidence, it shows it in this warning sign, where developers when you click on it, it shows that I expected this to be in the program, but was not expected. And the idea here, we do want developers to explore other relevant hypotheses, but at the same time, we want to signify that these hypotheses, this hypothesis might not be correct due to this lack of evidence. Let's do a demo of the tool. I will just show you how it looks like in a real sample. Okay. Okay, we need to quick. Yes. Go away. All right, so the interface of hypothesizer looks like this, and the bug is basically just dimension of the bug is the same one. When you search in the movie and click search, it doesn't show anything, right? And to debug in using hypothesizer, you need to record the reproduction of the step. So I will click Spider-Man and then search, and then hypothesizer will start hypothesizing or thinking, which is basically doing the same thing I showed you in the slides. hopefully it's going to show us some results very soon. All right. So now it shows this description, which is telling me, I found some hypotheses, but help me more to narrow down these relevant hypotheses if you select what your symptom is, what you're observing. And because I already know that the server, the code is fetching data from the server and the data is not showing, I would say enable to render data fetch from the server because I know that there's data, but it's not showing there. Then this is going to show me a hypothesis saying that data received from the server is not being parsed. When I click on it, it shows this list of evidence, just like I showed you. For example, it shows this networking happened, and the payload here is the movies. So everything work as expected in these steps. But I need to parse the data based on the hypothesis. So I will go and click show in editor, which is a feature of hypothesizer I did not show. But if you click in this, hypothesizer can open up exactly where this evidence is located in your source code. So you can jump right into where you need to test the hypothesis rather than navigating. So let me go back and see. Hypothesize they use the JSON API immediately after the fetch. And give me a couple of resources to read more if I don't. But let me do exactly what the hypothesizer said. So that's what hypothesizer said. So the hypothesizer said, now rerun the program. And the bug is fixed. And the idea is now, it's helped me to find the hypothesis and tested it from the beginning to end. It was with me, the debugging hypothesis, the debugger was with me throughout the debugging process, rather than having been a tool that I used in one part of the debugging or to do a certain activities. So I need to test the hypothesizer in a control experiment and see if it does help or not. So to do that, I went and created a dataset of hypotheses containing 10 different hypotheses for web application. I gathered information about these hypotheses from my experience in Stack Overflow and other web application resources. I mean, so it contains pretty much the things I show you: defect symptoms, list of hypotheses, and the condition, and other things, but I did not show it in the table. I recruited 16 professional developers. My inclusion criteria that developers had to have at least 1 year of professional experience and have some experience in web development. The average was 20 years of experience for each category. And I give the participants 2 debugging tasks. One with hypothesizer, only use hypothesizer, and the other, you could use pretty much everything. You could use Stack Overflow, the debugger, anything you use in your day-to-day. And what I found, that hypothesizer dramatically improved the success rate of fixing the defect by factor of 5 and decreased the time to debug by factor of 2. What does that mean? Let's see a table that and give more detail about it. So in the control group here, you see can developers use lots of different types of tools. They use the log, they use breakpoints, DOM inspector, network inspector, reactive tools, online resources. So that's not surprising. We already know that developers engage in different type of activities when debugging is become longer. But in the experimental, they only use hypothesizer. The success rate when they did not use hypothesizer was very low, was 19. While in the experimental, while using hypothesizer, 100%. The average time to fix was 21 minutes to fix the bug for those who fix it. And for all developers who use the hypothesizer, the average time was 8 minutes. The average file view was 4 compared to only 1 file within hypothesizer. The average program rerun you remember that run cycle was 11 times for developers without hypothesizer, and with hypothesizer was an average 3 times. So that brings me to my thesis again, and I believe that I defended my thesis. I proved that I at least have evidence that suggests that offering tools supported by hypothesis-based debugging that help developers find test hypotheses significantly improve developers' efficiency. All right. I want to also touch on the few ideas for my future work. So I believe that hypothesizer will be working right away with ChatGPT. Everyone's talking about ChatGPT, so I had to think about how to incorporate ChatGPT within hypothesizer. So one idea I had was, the how to fix was simple, really. There's no program synthesis in it. It's just trying to suggest developers a code snippet they need to adapt in their program. So the idea, what if we use ChatGPT? If we give ChatGPT this how to fix, and the ChatGPT basically will spit out a more personalized, customized to that defect steps that developer can do. I think that can also dramatically help developers quickly test these hypotheses. The other thing is about the data set of hypotheses. Hypothesizer without the data set basically is not very effective because it doesn't know how to reason about the code or to think on other hypotheses. So hypothesis data set is central to hypothesizer. And to scale hypothesizer to working with other different bugs, we need to add more hypotheses. And the way I did it for my study, I did it manually, going Stack Overflow and my own experience. But Stack Overflow has a lot of information, and it has different type of posts that basically are addressing the same underlying symptoms or underlying bug. So if we group these different Stack Overflow posts that address the same defect and give it to ChatGPT and use this in-context learning, which is a fancy word to give it more examples for ChatGPT of what a hypothesis looks like. So give them a bunch of Stack Overflow posts. Please write a hypothesis that represents all these Stack Overflow posts that describe the same bug, but in different, very specific program. Write a general hypothesis. This is an example of hypothesis. This is an example of description. This is an example of conditions that, if satisfied, make the hypothesis relevant. This is an example of how to fix steps and things like that. And then let the ChatGPT create these data set hypotheses. We may need some sort of human in the loop here, where an experienced developers also review this data set hypotheses and improve it. But at least we may get the first kind of basic template done by ChatGPT. With that, I would like to conclude. I would like to thank my advisor, Thomas Latoza, for his time, effort, guidelines throughout the 6 years. Thank you so much. Thank you to my awesome committee for your feedback, interesting questions. Thank you to my friends and colleagues in the Developer Experience Lab for interesting discussion and feedback I got for all my papers. Also, thank you for my students or the students I work with, and so many other people that I cannot unfortunately fit in one picture. Thank you so much, and I'm happy to get your questions.
Thank you, Abdulaziz. So now, as is traditional, we'll first have questions from the committee, and I guess Dean Gooding, she'd also like to ask any questions. And if we have time after that, we'll have questions from the rest of the audience. And then after all that is done, we'll then ask everybody to leave, and the committee will have a private discussion. Maybe to get started, Brittany, would you like to go first?
Sure. Can you all hear me?
Yes.
Fantastic. Great presentation. Awesome research. I think there's a lot of really cool things that you presented here today. So really appreciate the effort that you've put into this thesis. One thing that I thought about that really I think I always think about when it comes to these sorts of things. So obviously the idea of hypothesis-based debugging and of course providing tool support in that vein are obviously useful from some of the insights that you've gathered here. But I think one thing that's also obvious is that a tool like Hypothesizer would introduce another step for developers and really another interface for developers to learn and make use of. So I'm curious if there were any thoughts from what you've already done or things you were thinking about for the future regarding how something like this might fit into developers' workflows. Like, were there any insights from your user evaluation or anything that points to that type of benefit?
Yeah, thank you so much for your question. I think I had some sort of discussion in this with different participants, and they described that Hypothesizer may really work well with developers onboarding. So example, if you have a developers who's just joined a project and there's this very common defects that happen in the program, and then you want to not only point out to different bugs, but also have this learning platform where they show the hypothesis, the evidence they need to look at for these things. So that one thing, how it may fit. But in general, I think Hypothesizer may just work as a debugger that, as a team, a team of developers can work and populate different kind of hypotheses so that when a bug happens, even if they have seen it before, but Hypothesizer can quickly introduce the relevant hypotheses for them without them going to these manual steps of having gathering information and coming up with a hypothesis. Would that answer your question?
I think so. So if I'm understanding, I think the use case of onboarding is actually a really interesting one. So thank you for sharing that. In terms of the other side of that, it almost sounds like it may not be necessarily, at least at this stage, something that would be every time I run my test, I'm going to Hypothesizer, but something where I'm really stuck on this bug. Let me pull Hypothesizer out and see if I can't better understand, or if the team can't better understand this defect. Is that kind of a use case that you're thinking?
Yeah, exactly. I think this is a good way to say it. I mean, if you know how to fix it, you may not even use the regular debugger to inspect the program, right? You will go right in the source code and fix it.
Yeah.
But if you kind of don't have the hypothesis and you don't understand why it might happen, and you maybe feel stuck, then yeah, Hypothesizer can help you find hypothesis. But I want to state something that prior work have shown that most of the hypotheses, at least the first few hypotheses that developers come up with, are wrong. So even though the developers eventually gonna fix the bug and find the correct hypothesis, the first few hypotheses may not be correct. So I may also argue that using Hypothesizer from the beginning, I'm not really relying on the idea of you need to generate a hypothesis, think through it first, is better way. Maybe just if we got Hypothesizer to have all hypotheses for sure, it's maybe a good idea just to start with Hypothesizer and then work collaboratively with Hypothesizer to identify the hypothesis, relevant hypothesis, correct hypothesis faster.
Okay, thank you for that. One more, just before I pass it on, I don't want to take up all the time, but I did have a question about your future work. So I always get excited, obviously, when people talk about ways that they can integrate ChatGPT and those types of technologies into their work. And I think it's a really cool idea to think about how it would fit in the scheme of what you're doing. One of the questions, and I had a couple questions there, so if there's time to circle back, I'll ask the other. But one of the questions I had was around the support for fix suggestions, which again, I think is a really cool idea to be able to have something that can aid in that process. But I'm curious if you've thought about what kind of experiments or studies you might have to run to determine how feasible or accurate or useful the fix suggestions would be that you might actually get from ChatGPT, both kind of on an anecdotal basis, but also at scale, right?
Yeah, so the experiment that I may conduct for this is just to see if working with ChatGPT gonna improve the way we built a data set of hypotheses. So back to the data set of hypotheses. So I may have a few experienced developers working with ChatGPT and Hypothesizer to collect Stack Overflow posts and then give it to Stack Overflow, Stack Overflow post and give it to ChatGPT. And the ChatGPT will suggest a hypothesis with a condition and a plan to fix. And then the experienced developer made some changes, and then I will have another kind of control experiment that just tests if this new hypothesis that was generated with this new interface and collaborating with ChatGPT will help developers fix the bug faster than, for example, going to the Stack Overflow again and having this traditional debugging route. I think that's one reasonable way to study it, not just focusing on this fix thing, but having the idea of testing the entire workflow, generating new hypotheses.
Mm-hmm. Okay, great. Actually, funny enough, you just answered the other question that I had, and I think I may have not clearly phrased this one, but I'm going to pass on to the next one. If there's time, I can come back to the other question that I had. Thank you so much.
Great. Let's do our other Zoom committee member.
Hello, I guess that's me.
Yeah.
Very great to see you, Abdulaziz. Really nice presentation. I really enjoyed it. I also have to comment that, like, in addition to having a great presentation of all of this work that has like already been peer reviewed at great venues, the discussion of future work, both in the thesis and also in the presentation, I feel like as I was reading that part of the thesis and as you were presenting it, I was like, darn, like there were a lot of easy questions that I could have had that are like, oh, but what about this kind of future work? And you're like, here's the sketch of what it would be already. It's really exciting and great to see. So I think that the first thing that I would want to talk about, and we can have a like brief chat about this one, and then I'll yield, and if we come back again, we can talk more, is about the role of hypothesizer and like collecting and sharing hypotheses depending on expertise level. So like I definitely get it that there's like tremendous value for novices where having a tool like Hypothesizer that presents these hypotheses helps transfer the experience from like the developers who know what the hypotheses are to the ones who don't know yet. What do you think Hypothesizer would look like if it was designed instead for like a different developer use case where, developer who like knows all of the hypotheses that could be and, just doesn't know which to choose from, or like how to keep track of what it is that they've done and what worked and what didn't work? Like, it seems like they might have different needs. Is it something you thought about or could speculate on?
Yeah, so I guess the question is about helping developers determine which hypothesis to start with. Yeah, like that. I think that's maybe also an important aspect of Hypothesizer, and I believe that yes, keeping track of these hypotheses and going back and forth between different hypotheses also may mandate like some changes in the interface and having some new functionality of Hypothesizer. But I also believe that even for for developers who have all the hypotheses, if that developers exist, but let's assume that developers know everything and have every hypothesis in their head. It's actually, I think it's beneficial also to have some automated tools that do the work they probably gonna do to arrive to the hypothesis. So even if they have a hypothesis, like, hey, the parsing may not be correct, so let me go and check it. They need to go and look at the source code. They need to fire the debugger. They need to inspect. They need to do all this manual work. But Hypothesizer can do it automatically and much more. It shows it in one interface, and it can also propose other hypotheses that the developers may eventually do it. So it does it in parallel. So it's not one experienced developers working thinking in sequential manner and doing in sequential manner. The tool itself is parallelized. has multi-threading. It does think it's in different, faster way. So I think that's also beneficial for developers who's experienced in having everything in their mind. The other way is could be that developers may, I have to think about it, but what if the developers already have a hypothesis? So it just need the hypothesizer to collect evidence for that hypothesis. Not really, I don't really care about other hypotheses you have. So it's maybe a good idea to have the interface with hypotheses and developers that search in text. And they click, show me this hypothesis, investigate this hypothesis quickly for me. So rather than investigating a lot of hypotheses, just focus on this and collect all the information that developers may need to do it manually. So that one way to even have this experienced developers benefits. Okay.
Cool, thank you. Maybe as a follow-up, I'll take one follow-up. At what, well, okay, sorry, I'm trying to make it just one. What level of abstraction do you think, oh, okay, sorry, I've been thinking about a lot of different questions. I'm picking just one, I promise. Are you aware of any existing like empirical studies of the information needs that developers have when debugging? I guess like aside from the kind of observatory stuff that you have done, like maybe other related work. And if we wanted to conduct such a study where we looked at developers like really maybe stratified across different tasks where they're debugging different systems written in different languages and they have different backgrounds. Like, do you think that there is a valid methodology to conduct such a study that might bring some insights for next person's thesis?
Yeah, so to rephrase your question, so I make sure that I understood it, that you think that information needs or how developers look for information may depend on the type of the programs and the implementation details?
Yeah, specifically for debugging. Yeah.
For debugging. Yeah, I believe so. Yeah, I believe that, you know, having a backend in multi-threading environment, developers may be interested in investigating and looking for different information than mobile web applications that mainly depend on event in the interface. So the type of information may differ, like maybe these people in the interface concern more about event-driven information, like if I click this button, what would happen, things like that. The others, other type of information, but I doubt it if you like in a very abstract way or a general way that there are fundamental differences, because prior work looked at the type of questions that developer ask while debugging, and these type of questions represent information needs. So why this happened is cause-effect kind of information. You're looking for a cause that made that change in the output in the program, whether it's an interface or an input to other function. So I believe that essentially, fundamentally, there's no changes. So if you look at different kind of things, you may end up different kind of application in debugging. You may end up with the same type of questions. Why? What is this? And why did that happen? Why this program is producing that type of things that I don't expect? In a very general way, they are the same, but for specific things and detail information, they differ because at the end of the day, the programs differ and the output differ. So there's the specific type of information, they differ as well. Yeah.
Awesome. Thank you so much. I'll yield my time to the next committee member.
Great, Professor Offit.
Thank you. Thank you, Abdulaziz, for a very interesting presentation and a very interesting thesis. You know, I want to call out one thing. It was a very clean thesis. Almost no typos, errors. There are a lot of clumsy habits that I see from people a lot that you just don't have. And I really appreciate that. Nothing else is like the usability, makes it easier to read it.
Thank you.
I didn't even see where you used citations inappropriately, which a lot of people seem to do that in professional. We even didn't know if you used that slash. Be too lazy to decide whether it's man in the north. So I appreciate it. Also, you know, as John said, some good papers, good places. I would have liked to have seen an explicit list of papers in the thesis somewhere. I don't know if I missed it. I think you had a slide early on
Yeah.
with that. You don't need to find it. That's fine. I think I saw 4 published and 2 submitted. Is that basically?
Yeah.
That's what I meant.
Oh,
Just very cool.
Yeah.
They're really great, yeah.
yeah, that's more. That's
I just submitted one to West, and I have one in the empirical software engineering. These are 2 in submission.
good journal. That's, is this the first submission?
This is the second review. I'm expecting a
It's
second.
in revision. Okay.
I had a major revision, but hopefully got my minor.
So, well, once I get a revised submit, whether it's major or minor, I assume it's published. Can't officially put it somewhere, but that means, to me, that means published. Also, I found the reference, thank you very much. Paper from 1982 by Art Debuggers. Debugging behavior. It seems like it was a little bit later, but I read either that paper or another paper he wrote a long time ago, and it really affected how I taught programming early in my career, because it very clearly let out the differences in how people talk. It's one of those things that stuck with me, but I completely forgot what the paper was. So I appreciate you finding that paper for me. So I do have a couple of questions. So one question is, and I think that may have been in one of Jeffrey's papers, not that paper, that the finding was that programmers often would make an initial hypothesis, make a change, didn't fix it, and then they would leave the change in itself. So I didn't see that. Did you observe that? Did you look for that? Is that still true? Is that? And often they would leave an incorrect.
Yeah, I did not focus on that particular thing, so I did not really. Maybe there is in some of my study that there's some instance of the behavior. This is an interesting behavior, but I have seen other papers talk about it. Thomas Ladoza also have a paper that said that inexperienced developers introduce bugs when they change while the experience maybe fix the bug faster. And I think I talked to other professor about that. They say one of their observation was the developers or participants made changes and then they will leave it. And then after that, they would say this hypothesis is incorrect. And then further, they will come back to the hypothesis, leave this change, and then investigate the same incorrect hypothesis again. And that accumulate like the bug and with the incorrect hypothesis just will lead them way away from the fix and make things worse. But for me, I did not observe this or I did not focus on that particular thing.
I certainly observed that when I was teaching programming. I have done for quite a while. I would see a lot of students who did that. Those are the students who didn't do well. And sometimes I could intervene and convince them not to do that, just have better behavior, and they would suddenly become good programmers. So that, okay. So you think you didn't really focus. There's also a question of how many hypotheses do programmers go through before they find the correct hypothesis, a correct hypothesis, often many ways. Were you able to quantify that?
Yeah, so for the first study I did, one of the observation I had was for I did not present this, but for the group that did not receive any aid, whether it's false location or potential hypothesis. I asked developers to state all their hypotheses before investigating. And I found that the maximum number of hypotheses that developers came with was 3. And on average, they come up with 1.5 or 2 before fixing the bug, or even just giving up, not knowing what to do. So I would say that developers often will not generate so many hypotheses. Either they get it from the first 2 or 3, and then they get stuck.
Is that influenced by the size of the program? More code, more hypotheses?
I would say maybe, but developers often, when they debug, the size of the program does not matter if they know exactly the program they debug. And if someone has no experience, haven't seen the code base yet, the entire program may be related to the bug. But an experienced developers who have worked with the program, even if in 1 million line of code, they know that the bug, this is in this component of maybe 1,000 line of code, and it's either in this thing or in this thing. So they somehow have this context and defect context they had in their mind. But yeah, so it depends the number of hypotheses the developer have based on the program, and depends on their experience. So, but essentially, I would say the experienced developers, the number of hypotheses they formulated, if they know the code base, is not impacted by the size of the program, but because they already have narrowed down which is really related to the bug.
And is that pretty accurate? So I have many lines of code, I have whatever, 50,000 modules. And then I think, well, it's in one of these 3 or 4. Are the debuggers usually right in the hypothesis? Because that's a different kind of hypothesis. So they're usually right, always right. You know, it's okay if you did.
I would say, I don't know, but prior work has suggested that the first few hypotheses often not correct. Based on the studies, but yeah, I don't have a very specific answer for this.
So another thing I was thinking of is the different levels of bugs and software. And this is probably too simplified, but the little clips where I just write the expression wrong, use the wrong variable. Something small, kind of like the things that APR fixes as well. Or then there's things that as a programmer left out. I forgot to handle this. I forgot this might happen. And then there are more higher level problems where the design is flawed. So the design will work to a certain point, and then I need to redesign the software. From certainly from fixing the program, those are really good. And also, it seems like they're probably different from a debugging perspective too, but I guess I'm not totally sure. What kind of mistakes were you focusing on? Did you like try all 3 of those, or maybe there were more? I don't have a full conversation.
Yeah, so I did not really try to categorize these bugs, whether they are fundamentally designed or very specific. The way I curated these bugs all by looking up bugs that reported in Stack Overflow, because these are what developers experience and struggle with. And my idea was developers really had to go and ask experienced developers in Stack Overflow because they lack a hypothesis in the first place. And then this bug may be a good potential bug to use in my study because I'm concerned with these hypotheses. But yeah, I think it's interesting to consider these design level bugs versus implementation bugs, and how hypotheses might help, and how detailed hypotheses may need, and all this stuff. I think it's interesting.
So were most of the problems with that, would you categorize them as small coding errors or mission?
Yeah, so the bugs, I did were in terms of lines of code. They were, often 2 to 3 edits in the source code. So remove these lines and edit these, lines. So, the bugs aren't really like changes in, like in multiple files or having to implement a new component or something.
I think that's the kind of problem where any kind of automation is still pretty far away.
Yeah,
Like my car can help me park, but it's not gonna drive.
yeah,
In your study, do you think you had enough programmer subjects?
well, I did different studies, and you can see that I used different type of methodology to recruit people. So my first study, I used George Mason's master students. So I recruit from master students. That was relatively easy to do.
Here.
Yeah, 20 people, and then I had to do interviews by sending out to professional developers. That was hard. I barely got 10. And I had this live stream programming where I used this data. I talked to some people there. The response rate was low. And the last study I did, I got 16 professional developers outside from Mason. I was a struggle to really to recruit them. So the numbers I believe are enough. I observed the significant differences based on these number I had, and I got answers for my questions based on the population I had, and so I think these are enough numbers. And we could argue is 16 enough or not, but if I observed differences and these differences were significant, I think then these worth reporting and sharing with the community. That's kind of the way I go with it.
Yeah, so that's let me ask this as a broader. Something that our
Mhm.
so almost all. What's a represent? Programmers or users. Will we ever be able to figure that out? How much easier will that make our research? I'm not asking you to solve that.
I don't know. I don't know. But, I always get some feedback, reviewers. So one of my studies reviewers said, 20 participants aren't enough. I did within subject design, meaning I got 60, I got 60 point of view because if each participant did 3 tasks. And they said, that's enough, that's not enough. What I did as a rebuttal, I reviewed 5 years publication in the same venue. And I said, look, the average for these studies is 10 or 15. I did 20. That not enough is, we could argue like for a long time, we don't know what enough, but it seems that the community agreed that anything above 15 is reasonable. And that got accepted.
That was a rebuttal for a conference.
Yeah.
Wow. In a journal response, I would think you'd have much better case, much better chance of winning that argument.
Yeah, it's just 2 days, and I was like, how I'm gonna convince them that 20 is enough? It's a good idea, maybe say like, look at all these published papers that have the same range. I mean, people in other fields have more kind of rigorous statistical method that they do this power nation, or I forgot its name, but I haven't seen that used enough in software engineering. So maybe that's a way to go with it, just to determine the statistical power.
Well, there's some statistical data only valid if you have.
Mhm.
And I see that like that used in public opinion,
Okay.
which is pure nonsense. We don't know whether. I don't know if we ever will, but I think we probably need to. Clearly beyond. Okay, anyway, that's enough. I wanted to go there. philosophy.
That's great. I have to comment on that. So thank you so much for the presentation. I think it was very clear. It has a clear motivation in research and the contributions are there. This is well written. Thank you for all the care. I have a few questions about the population too. So in the first study, you reported that life, and I was wondering if this sample for you has a specific bias or limitation. Like, I have the impression that these are people who are experienced and they are very proud of what they are doing. So did you know, and you mentioned that you have different approaches to collect data. So did you notice like an impact of the profile of like how homogeneous are the programmers that you recruited for the first study versus the other studies? Do you feel like impact your data by the outcome?
Yeah, I agree, because I use different type of recruitment, different type of population. But each study has different type of goals and research question, and I believe that each research question align with the methodology I follow. For the live stream programming, I try to follow kind of criteria I set to recruit or get a representative sample. So for instance, I had to watch the entire stream before I decide if this is going to be in the data set or not. And I had to see that it doesn't contain more than, I forgot the percentage they have. I think it's 5% of non-development work. So I would allow like 10% of interruption going outside of the stream, because although I'm gonna take out these interruption and things, but I still believe that context switching may impact work. So I don't want to have the stream that, I don't know, 50% of the stream is talking about different things, which may happen. I mean, even developers, when you observe them in their work, they may got one day spend in one day just talking to other people, not doing anything. So I just wanted to get a representative sample of developers working and debugging. I don't care if they talk maybe 5 minutes here and there, but the majority of the time we're focused on debugging, because my study focused on debugging and not really how developers spend their time. So I don't think I don't care about if the way they spend their time is representative. It's just do they have enough debugging time, and that debugging time was not being interrupted a lot. Do they work in a task that is representative, reported in GitHub issue? Are the project they're working on end up in production? All this kind of stuff I did and had this as a criteria to make sure that the debugging task they worked on was representative of real world. But I agree there is some sort of still some doubt and limitation of this new source of data. But hopefully with more researcher using that data, we can understand how to use it more better, and whether or not it's representative. I believe it's representative. But still, like, people still having the same argument. I get this in the review comments as well. Yeah, that answers the question.
Okay. Actually, in your thesis, you also mentioned that or that hypothesis. Can you talk a little bit about the selection of these criteria? Like you cannot study the efficiency if they are talking out loud or being interrupted all the time. Why efficacy instead of effectiveness, or what metrics usually are included in that?
So the things I ultimately measured in hypothesize whether they fix the bug or not. So if they fix the bug and demonstrate that they fix bug, meaning they reproduce the bug and the bug was there, not there, then that's the ultimate goal. But I also looked at how many files they navigate to when debugging, how many times do you rerun the program, how many times they switch between different type of tools. And all this like impact the performance of debugging. If they have to switch between so many different tools, they have to navigate so many files, they have to rerun the program so many times. They aren't so effective in focusing and fixing the bug faster, I guess. So yeah, that's the way I looked at debugging, if that answers.
Yeah, it's interesting. I think the efficiency is somehow included in the measure of
Yeah.
performance. Not necessarily looking at the time, but the effort that they put,
Yeah.
the resources that they have to look at.
Exactly.
Yeah, another question I have is how similar to what Jack was talking about, the nature and the type of faults that can be covered by the tool that you're proposing. And specifically, I was wondering what projects and the cycles that you analyze, the number of cycles in the lane are linked to the scope of the code or purpose of the application that they are building. Isn't it related to the complexity of the bug? Like sometimes you have just a syntax error, like semicolon here versus there is a logical error that will require another loop or another comment there. So can you talk a little bit more about this link that might be between cycles of testing, debugging code, and the specific nature of the bug?
Yes, I agree with you that may be more complicated by, and if we define complication about is how many lines of code. I don't know if that's the correct definition, but how many lines of code developers have to add or delete to fix the bug? Then I don't have evidence, but I think is that the more developers have to edit and add, maybe the more they need to test and refine their hypotheses. And I think I don't think hypothesizer has any sort of limitation in terms of how complicated the bug is. Essentially, the idea of hypothesizer, I just needed to have or to offer the developers the correct hypothesis, saying, you need to implement this API, or you need to implement parsing, for example, or you need to handle the click event. And turns out that implementing event, click event need few lines of code. So that may be a complicated bug because it has to add a few lines of code, but the hypothesis is the same. Now, to implement that and test if the hypothesis is correct by implementing the fix and testing it and see if it's fixed the bug, developers may need maybe deeper understanding. It's not simple things to change. They may need to think about how to add this line of code within the project. So that all may impact the entire debugging process, and they may need to refine it multiple times. But hypothesizer may help, especially in the future work. It may help if we incorporate ChatGPT and having a suggestion within the context of the program, and developers see the entire edit as a suggestion, and they can easily imagine how it can fit in their program. So that may reduce the edit run cycles or the time the developers need to investigate.
Thank you.
Guess I'll ask a couple questions. So what would happen if you had like 10,000 hypotheses? Do you have any evidence from like the evaluations or studies you've done about how precise hypothesizer is? I mean, it's useful to the extent you can find the right hypothesis fast, but like the extent that developer had 500 different hypotheses to look through, it's not quite as helpful anymore.
Yes, so I did a case study in one of in the paper I submitted, but I did not show it. It's in the thesis, but because at the time, so what I did, I went and had 10 bugs that represent the 10 hypotheses I had in the data set, and reproduce it twice in different programs. So I got 20 programs with different sizes, a line of code, and run hypothesizer across the 20 programs. Just to see, can hypothesizer find the hypothesis based on the evidence and the condition it has in the data set, and how much time it gets, and how accurate it is. And I found that, yes, the hypothesizer found all the correct hypothesis in all 20 cases, in an average in 10 seconds. So now the question is, if I scale this to 100,000 and 1 million hypotheses, will hypothesizer be able to identify the correct hypothesis? From the case study, I would say yes, but the hypotheses need to be well defined in terms of condition. So you don't say, for example, if you find this line of code, then the hypothesis is that is this. I think if you have a not well defined condition, like that the evidence that develops fine, you may end up with a lot of hypotheses that develop need to manually investigate. But if you do describe the hypothesis and have enough evidence that distinguish it from other type of bugs and other type of instances, then I think we believe that hypothesizer can be accurate in identifying the hypothesis. But this is maybe a future work that's working when we have a larger data set of hypotheses in my future work, and study how hypothesizer work with it.
Great, thank you. How do you end up with the set of events that you decided to log? Like, what was the motivation behind the things you were focusing on, and what you sort of decided to include in the program to get your trace?
You mean in general or for a hypothesis?
Yeah, just for the things that your tool hypothesizer logged.
Okay.
How did you decide on choosing those things and not something else?
Well, I basically tried to log everything I thought might represent a good evidence for a hypothesis. So I thought about source code is important. Execution trace, meaning which functions get called, is important. All sorts of event in the interface is important because web application is full of interactive events. So it has to be there. I thought about networking activities because web application has all sorts of networking activities. I thought about changes in the UI because a web application mostly UI driven, meaning every interaction like impact the UI somehow. So based on just brainstorming about what kind of evidence I had, I just did it. But however, hypothesizer can collect anything that happened in the program because it's controlled by Chrome browser. So it has, if any other information it doesn't have now, it can certainly collect if it is within the program runtime or program behavior. But initially, this is how I come up with the list of things to log and instrument like that.
Great, thank you. All right, I guess Dean Gooding, would you like to ask any questions? Are you still there? You put that participant to back up.
She's there.
Okay.
Okay. So I don't have any questions. Very interesting piece of research. Really impressed with the back and forth between the candidate and the committee. So that's all for me. Also, my internet seems to be unstable. So thank you.
Great. Yeah, so we maybe have a couple of minutes if anybody on the committee still has any pressing questions that they'd like to still ask.
Nope, I'm great. I really enjoyed hearing the whole and participating in this conversation.
Same, I'm good here.
Okay. right, I guess we'll ask everybody except for the committee, I guess, and Dean Goodings to lead. And we'll